Good morning. Good to see you again. Today we're going to take a little bit of a kind of a detour and talk about another area of complexity theory called algebraic complexity theory. So I'm going to try to cram everything about algebraic complexity theory that you might want to know into like 1 or maybe 1.5 lectures. That's a little bit tough because the standard reference for this topic, this book, is like 600 pages long. So it's longer than our own textbook. But well, I'll tell you a little bit what you need to know about in this subject. If you recall, last time we were talking about the permanent and all its glorious properties, one of which is Valiant's theorem, which is that it's complete for this complexity class p to the sharp p. And I punted on actually showing that proof. I'm going to show it later in the course. But in this lecture, we're going to see some other algebraic complexity classes, including one for which the permanent is complete. And we'll also not prove that fact either. So it'll be a little thematic to consistently not prove these completeness results. Okay, so algebraic complexity theory is kind of a mathy topic, which in a way like kind of predates the complexity theory that we've been studying with like Boolean functions and Turing machines and so forth. And it's all concerned with the kind of things that like ancient mathematicians would think about, namely how many arithmetic operations are needed to compute something. Okay, and eventually we're going to be studying this in the model of arithmetic circuits, which kind of look like this. I'll come back to it shortly, but let me talk about some of these motivating questions first. Okay, so actually in some sense the question that motivated this whole area originally from the 50s is number one, how many sort of operations does it take to evaluate a polynomial? So for example, let's say you have in your hand some explicit polynomial like this. Okay, and you know like the coefficients ai, and you know the variable x, and you just want to compute the value of the polynomial. Well, there's a naive way to do this. This is the first way you would think of, which is compute x squared, x cubed, up to xn by multiplying x by itself. That's the n minus 1 multiplications. And then once you have that, you can compute ai x to the I for all I. That takes you another n multiplications. Okay, so basically 2n multiplications. And then add it all up. Okay, and that's n additions. Okay, so that's the way you would first think to do it. Okay, you have to do 2n multiplications basically and n additions. But there is a more efficient way to do it. Perhaps you heard of it. It's called Horner's method. I guess he was some ancient mathematician. And it's just this trick. You can instead compute it like this. A0 plus, oops, I need an x in there. X times A1 plus x times A2 plus x times A3 plus, let me get the ending correctly here, an minus 1 plus x times an. Okay, if you haven't seen that before, take a look at it. You basically see that this also works. A3 gets like 1, 2, 3 copies of x times it against it as desired. And how many operations do we do? Well, actually, the beauty of it is we only do n multiplications and n additions. Okay, so if, doing those multiplications is kind of a drag, well, you just saved yourself about n of them. And this algebraic complexity in some ways was started with the mathematician Ostrovsky, who in 1954 conjectured that in some sense this is optimal, that you always need at least n multiplications, even if, actually he said or divisions, even if plus and minus are free. He basically said there's no way to do this without at least multiplying n times. And seems hard to do it otherwise, but actually it took about 10 years to fully prove that conjecture. So that's a little example of algebraic complexity in action. Okay, let's take a look at this next one, motivating problem. You have two polynomials, and you want to multiply them together. So basically, you want to compute the coefficients of the result. If you think about it, like how do you get the ith coefficient? It's some kind of like convolution of the a's and the b's, right? So it would seem to take about n operations to get the ith coefficient. And you have n coefficients, or 2n coefficients that you need to get, something like that. So for this problem, the naive method seems to take like order n squared operations, additions and multiplications. And actually, the great mathematician Kolmogorov in the 60s, in some sense, you can think of it as he conjectured that this is tight. Actually, Kolmogorov is not interested in multiplying polynomials. He's interested in multiplying integers. It's quite similar, right? If you take x to be 10, then this is some integer, this is some integer. You want to compute the coefficients, aka digits of the result. So he conjectured, you can think of it as though he conjectured that, but in fact, Karatsuba showed that that's not correct. And in fact, you can do it much better. You can it's doable with n log n operations. I guess that's fact is due to Strassen and Schoenhage. And how do you do it with n log n operations? In case you don't know, it's bullet point 3. You do it with the discrete Fourier transform. Actually take the discrete Fourier transform of the coefficient sequences, then multiply the results together pointwise, and take the inverse discrete Fourier transform, which is basically the same thing as the discrete Fourier transform. And well, doing that takes order n operations plus the amount of time to do a discrete Fourier transform, which is multiplication by this specific n by n matrix, multiplying a vector by a specific n by n matrix whose entries are roots of unity. Multiplied n by n matrix times a length n vector seems like it should take n squared operations, but due to the glorious structure of the DFT matrix, you can actually do it in order n log n operations by some kind of recursive method called the fast Fourier transform, invented by Cooley and Tukey, and also by Gauss. So that's kind of neat. So it's a topic studied in algebraic complexity theory. This one, number 4, is very famous, both in algebraic complexity theory and in just regular complexity theory. It's kind of similar. If you have two n by n matrices, of course, you can multiply them together with n cubed steps. But there are these famous algorithms like Strassen's algorithm from the 70s that does it in basically n to the log base 2 of 7 steps, n to the 2.8 or something. And there have been many works on this topic to improve it. The latest of which is due to Legal in 14, which multiplies two n by n matrices in n to the 2.3728 something number of steps, arithmetic operations. OK. And computing the determinant and computing the permanent or other natural questions in this area, you have some kind of formula involving matrices you want to compute. How can you do this efficiently? OK, so maybe I hope this is giving you a flavor of the kind of stuff that gets studied in algebraic complexity theory. You kind of see it's kind of the mathy version of complexity. How many pluses and minuses and times and divides do you need to compute some quantity? I should mention here that perhaps on one hand you might think of it as not so realistic, because I suppose eventually in real life there's actually a cost to doing a multiplication or a division or an addition that's not just one. You have to actually, the numbers are very complex, just doing one operation would take a lot of time. But well, algebraic complexity theory kind of says, don't worry about that. Let's kind of stay at a higher mathematical level and just count these operations as costing 1. OK, so in fact, if you can prove lower bounds for the complexity of solving problems in this model, then it's great, because even if you disregard the complexity of the arithmetic operations themselves, you can still sometimes have lower bounds. OK, so the basic object to study in algebraic complexity theory, well, there's no kind of Turing machine. Instead, we work with circuits. So the basic model of study is an object like this, which is algebraic circuit. OK, and what's the deal with an algebraic circuit? Well, it's a circuit, so it's like a DAG, a directed acyclic graph. And the nodes have the internal nodes have 5 kind of labels, which are plus, minus, times. I'm sorry, that looks like an X, but these are times. I could use a dot, but anyway. Division, And the last kind is like multiplication by a scalar, which I wrote as times c. Like in this example, we have like a times 1/4 gate up here. That only takes in one input. And the inputs, these are scalars. Let me write that. And the sort of inputs are called variables, which I'm going to write as like capital X1 through capital Xn. And I should mention that these scalars are coming from usually a field. Okay, so really when you specify an algebraic circuit, you have to also specify like where the, the numbers are coming from. It's usually a field, so you can have all our nice operations. And let me mention that if you define, arithmetic circuits over, let's say, F2, the field of size 2, then it's really just the same as Boolean circuits, because like multiplication is like and plus is like XOR. It's also true for any finite constant size field. So generally in algebraic complexity, we work with infinite fields, or imagine infinite fields, like the reals or the rationals or the complex numbers. And it turns out to also be convenient for the field to be algebraically closed. All of which I'm just saying, like, let's just say the field is always the complex numbers unless otherwise specified. Okay, that just makes everything relatively simple. But it's not going to play a big deal in a big role in anything that we really talk about. A few other aspects of this story, which might be a little bit funny. Yeah, in all these problems, okay.
So you cannot add the constants, right? There.
I guess you should also be allowed to have 0 and 1 as leaves. Or you can have addition of a constant too.
Why you don't just allow like a constant, as we allow in the normal circuits, just like as a fixed hard-varied constant inside?
You could allow that too.
Right? Okay.
Yeah. Okay, so yeah, maybe I should have allowed that. Let's say.
Instead of multiplying by a scalar.
Sure.
Because then you don't need even.
You can either allow 0 and 1 as constants, and then you can multiply them by a scalar, or you can allow plus a constant. Okay.
You can generate 0 from x1 minus x1 and generate 1 by x1 divided by x1.
Okay, you can do that too. Yeah. Phew. Okay. So of course, all these things make a difference only of constant factors, which we're going to end up ignoring, despite the fact that in this motivating example, I actually cared to count things exactly. Another thing you might worry about is division by 0. And let me just say, don't stress about division by 0, okay, for the purpose of this talk and lecture. And there are propositions and lemmas to the effect of the fact that you don't have to stress about division by 0. But to kind of motivate why it's okay, let me actually tell you that instead of thinking about a circuit, an algebraic circuit, instead of thinking about it as something that maps like numbers to a number, like imagine plugging in complex numbers down here and evaluating the circuit, you should actually kind of think about it instead as mapping variables or indeterminates into a polynomial in those indeterminates, or a rational function. A rational function is a ratio of two polynomials, which you can get if you have division. So you see, if you kind of notice, let me emphasize the word formal polynomial up here. All of these problems I mentioned are actually about computing polynomials in some sense. For bullet point 1, if you think about both x and the a's as indeterminants, so you have n plus 2 indeterminants, then this expression is a polynomial in all the a's and the x. And you would, your Horner's method circuit for computing it, can treat the a's as indeterminants as well. Again, each coefficient here, each ci, in the output is some actually degree 2 polynomial in the a's and the b's. So here you should think of the input indeterminants as the a's and b's, and the c's are degree 2 polynomials in them. Similarly here, right, if you're multiplying two matrices, A times B, you would think of A and B as each n squared indeterminates or variables, the entries. And then your desired output, like Cij, is this degree 2 polynomial in the indeterminates A and B. Okay, so I want to sort of stress that you can think of, you should really think about algebraic circuits ultimately as computing either polynomials or, if you have division, rational functions, and just treat them like as formal objects. And therefore, that's why I say don't stress too much about the issue of division by like the scalar 0. Okay. Good. So that's algebraic circuits. Let me also put up one more definition because we kind of like it a lot. It's the same as in Boolean complexity. An algebraic formula is just the case where the circuit is a tree. In other words, all fan-outs are just 1. Okay, it's the case where you're not allowed to reuse intermediate computation. You have to like reconstruct it. And it corresponds to actually like formulas that you write down on a piece of paper. Like usually there you have to like specify like all the expressions and duplicate them if necessary. By the way, does anybody know what polynomial this guy computes? Okay, I'll let you calculate it while I erase the board. Yeah, it's x1, x2. It's a funny way to compute x1, x2. You could have done it with 1 multiplication, but decided to get fancy.
Can I ask,
Yeah.
just like some confusion, I cannot formulate the question like really precisely. But then, when you do this computation, like when you want to compute like the product of 2 matrices, for example, you can do a bunch of if statements. And if you do a bunch of if statements, like the output of the circuit is no longer a formal polynomial in the original variables, but like it's something different, no? Yes?
So we're working in this model algebraic circuits where there are like no if statements. So there's just these operations. But you can still, okay, matrix multiplication, there's a little bit trickiness is that it's a multi-output thing. There's n squared outputs. That's fine, so you have n squared outputs. And yeah, it's just like you need to compute these polynomials. So one way to do it, right, is you can do all these multiplications for each k. That's like k, n multiplications, and then add them all up. That's like another n. That's 2n gates probably, and you have to do this n squared times, so you have like n cubed gates. But also, like if you want to do like Strassen, if you think about it, you can you don't have to write it in like pseudocode. Like you can imagine like unfolding the whole recursion, and it would effectively give you a circuit of.
The Strassen, yeah, but like I'm just in general, it could exist the algorithm that like saying, oh, like if I have as an input the specific numbers, I can manipulate in those numbers like not in a formal way, but like oh, if I compute this expression, if it actually equal to this, it's not always the case, but like if it happens, then I can shortcut something and then.
Yeah, that's true. There are like more general models, things called like algebraic branching programs, algebraic decision trees, which take this into account. But
This is not inside out.
yeah, we're going to stick with chapters 1 and 2 of Burgesser, etc. I'm joking, but yeah. So this is like a very basic thing that's like kind of about the complexity of computing formal polynomials or rational functions. Okay, we also of course need a cost model. How much does a circuit cost? And there's basically 2 popular ones. So one is called total cost, and that's just each gate costs 1. It's kind of what you would expect. I mean, if you really want to get fancy, you can like have the times cost more than plus or something. But it's the simplest to just say each gate costs 1. And another cost model, which might look a little bit strange, but it turns out to be, just take my word for it, quite natural. It's called the non-scalar cost for some reason. Basically because it refers to the fact that you only charge for the non-scalar multiplications. Basically, it's just times and divide cost 1, and everything else is free. So plus, minus, times a constant, plus a constant, if you will, are free. Okay, you might think that's a little bit unnatural, but there's a couple of reasons why it turns out to be nice. One is that it does come up naturally. If you remember, Ostrovsky's question about the optimality of Horner's rule, he was even just like asking, you can have plus and minus for free, just how many multiplications do you really need? So it becomes a little bit natural. Another reason it's kind of natural is, for example, in Strasson's recursive algorithm, if you recall, like the thing that really generates this number, it's like a recursive thing where you like recursively multiply matrices. And that's actually controlled by the number of multiplications you do when you're multiplying those little 2x2 matrices with 7 multiplications. And finally, it just turns out it's like very natural to prove lower bounds in this model. It's like simpler. And then that's good. It's stronger. Like if you have a lower bound of the cost in this model, it's also a lower bound for the cost in this model. Question?
So in the total cost y, don't we also count the number of y's?
Here, OK, good point. I should have mentioned this. These are all binary operations. That's just traditionally how it's done. So the number of wires will be proportional to the number of gates. Good question. I forgot to mention that. So if you want to add n things, like you have to pay like n cost in this model. People also study variants where there's like unbounded fan-in, but again, let me just stick to this setup for simplicity. OK, so I don't know, to kind of warm you up to this, I'm going to do some simple examples. And actually, for these simple examples, I'm really going to focus on like, exactly how many operations are needed, which is, ultimately not what we really do in complexity theory. We eventually get to big O and stuff, but this will like motivate us. So here's a very simple example. Let's say you want to compute the polynomial x1, x2 times xn. Well, certainly size n minus 1 is sufficient. Actually, the fact that you need you use n minus 1 here is because the gates are assumed to be binary. You could do it in one gate if you allowed unbounded fan-in, but we don't. Just multiply them all together. Now you might ask, is this necessary? On one hand, like it would seem kind of crazy if you could do it better than that, but I don't know. You never know, right? Like here we use some weird factorization to get x1, x2. OK, granted we use 1, 2, 3, 4, 5 or something gates. But maybe there's some like clever way to do it that uses fewer than n minus 1 gates. OK, it turns out that there isn't, but it is necessary. And in fact, it's necessary even in the non-scalar cost model. So now, how do you compute this? You always need at least n minus 1 times operations. But I just bring up to say that like it's not overly easy to prove that fact. OK, it's like chapter 6 or something of this book. Yep.
Are you saying that we want to compute only one of the xn?
No, the product. The product. So you want to compute this degree n multilinear polynomial in the inputs. OK, so that's a little bit, well, reassuring that it's true, but a little bit unreassuring that it's apparently slightly tricky to prove. Let me also do another fun problem. Let's say you want to compute, and here I'm going to make things particularly easy. I'm going to give you a univariate polynomial to compute. You want to compute x1 to the power of 31. OK, I'm going to henceforth write x for this example. Well, you know how a natural way to do this, right? If you actually want to compute x1 to any like large number, you should use this repeated squaring trick. So I mean, you can compute x squared, then x to the 4th, and then you can compute x to the 8th, and the x to the 16th. This, for example, is you like plug this into this and this again into a times gate, and that's good. Now you have all the powers of 2 less than your target 31. And then you can like suitably combine the powers of 2 to get to this one. Actually, I select an example where it's a little bit annoying. You have to combine all of them. So like once you have all of them, you can multiply these two together and get x to the 24. Multiply this one and get x to the 28. Multiply this one and get x to the 30. And you have x, of course, in the input. So multiply that and you get x to the 31 and you're done. And it took you 8 multiplications.
You cannot save that, right?
What's that? Or can you?
Save it, right?
So let me just say, in general, like if you have x1 to the m, it's doable with at most 2 log base 2 of m multiplications. Right, because you spend the first log 2 base m multiplications to generate, the powers of 2 in the exponent up to about m, and then you might have to do up to another like log m combinations to put them together to get m. Yep.
Wait, this algorithm has a lot of if statements.
No, it has no if statements at all. So this let me draw a small example. This is the circuit. Here's the input. I do this like slightly funny thing where I allow, I have 2 fan-outs going to the same thing here. So now this circuit is currently computing x squared. And this circuit, sorry, that times is the same as x. That's a times now. This is now computing x to the 4th. And if I were to, for example, do this thing would be computing x to the 5th.
Oh, okay. I was thinking about the case where the exponent is variable.
Oh, yeah. Here, the exponent is not a variable. Like, imagine it's literally a constant. Yeah, thank you, yeah.
So then if you want x to the 6, like...
If you want x to the 6th, well, you can compute x squared, x to the 4th, and then multiply them together. That's 3.
Wait, so do we allow like an output to be like a goes to the several case or not?
Yes, in circuits, you're allowed to have arbitrary fan out. You can reuse internal things as many times as you want. We're actually going to make this observation that you cannot do this trick with formulas in 1 second. But check this out. This technique is not always optimal. So you can also multiply x by itself to get x squared. Then you can multiply this by x for whatever reason and get x cubed. Then you can square this and get x 6th, square that and get x 12th, square that and get x to the 24th. Now put your 6 and your 24 together to get x to the 30th. And put that together with x, and you get x to the 31. And you use 7 operations. OK, so this is again to show that, this is like saving one operation, but like, little tricks can go on. If you're interested in this stuff, you can like Google this phrase, addition chains. They used to teach it in 251, but like we dropped that topic. It's the problem of like what's the most efficient way to compute a specific power. Yep.
You also divide, right?
Aha, that's very good. I'm going to come to exactly that point as well. You have a question? Same question. OK, so if you're really smart, you can do this, x squared, x 4th. That's crazy x. OK, up to x. Well, let me write it. X to the 8, x to the 16, x to the 32. Then divide by x and get x to the 31. And that's 6 operations. And I brought all this up, in fact, to like show that it's funny. You're computing a polynomial. You're not computing a rational function. You're computing a polynomial, but it was actually efficacious for you to use division, which might not have been obvious, right? Your first thought. So that's why like division is allowed, because sometimes it can help you. Right. Good. So that shows that division helps. Let me also, come back to this earlier point. What is the formula size of this? So everything here has been a circuit. One reason it's a circuit is because, even when you square, you're using some, guide twice. In particular here, where like you use the liberty to like once you computed something like x6, you could use it several times. So the gates can have multiple fan out. In formulas, you're not allowed to have multiple fan out. You only have to have fan out 1. So for example, if you want to compute x squared, the picture has to be like this. OK, if you want to compute like x to the 4th, like you have to do, well, at least seemingly, you have to do this. So you're allowed to repeat the inputs. OK, that would compute x to the 4th. And for computing x to the 31, size 30 is necessary. And that's actually easy, because the formula size, or rather, the degree of the polynomial computed by a formula is always at most the size. Because with formulas, like every step, you can only increase the degree by at most 1. Because, well, actually, that's not true, right?
Oh, it's Actually, like you have like 31 leaves, right? That's why you should have at least 30 nodes to connect those leaves.
Yeah. Okay, maybe this, at first I thought this took like a 1-second proof, but maybe it's more like a 30-second proof. But yeah, this is like an exercise for you then, that like the largest degree you can get from a formula is at most the size of the circuit. And actually, we're going to end up liking formulas quite a lot. I mean, there's something nice about the algebraic formula model. And because of this, and also because it's kind of natural, in algebraic complexity, we focus just a lot on computing multivariate polynomials where the degree is polynomially bounded in the number of variables. Okay, so like a so-called P family, maybe the longer version of the name being polynomial degree family, is just a family of polynomials where Fn is a polynomial in n variables, or indeterminates, of degree at most P of n, where P is a polynomial. Okay. These are kind of like the analog of like languages in algebraic complexity theory. These are the things we're generally trying to compute. And as I said, we typically focus on the case where the degree is bounded in terms of the number of variables, polynomially bounded, both because it's kind of natural and because then it gives formulas the chance to compute these things efficiently. And if you recall, pretty much all the examples we talked about, the motivating examples, were in fact P families. Actually, I mean, sometimes you have to like mess around a little bit. Here I specified that like Fn always has exactly n variables. Like you could relax that to like some polynomially related number of variables, or you could do some stupidity involving like artificially forcing the number of variables. What I mean to say is, like, for example, evaluating a polynomial like a0 plus a1 x plus a2 x squared plus dot 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 plus a n x to the n. Here, there's actually n plus 1 inputs, x, and also we treat the a's as indeterminates. And the degree of this thing is like n plus 1, which is polynomial. In fact, it's exactly the same as the number of, oh no, it's actually one less than the number of variables. There's n plus 2 variables. Okay, so I mean, maybe technically, like this actually, the nth example like this has 2n or n plus 2 variables or something, but whatever, you can artificially fix that or change your definition. Or like for matrix multiplication, computing one entry, that's like a degree 2 polynomial, which is certainly polynomial in the number of variables, which is like 2n squared. Okay, so these polynomial degree families are the guys that we're typically interested in. One more example, and these examples will be very important for us, are like the determinant, the n by n determinant. So this is like the input is a matrix, so there's really like n squared variables. But if you recall, the formula for this is sum over all permutations of some number which is plus or minus 1 depending on the permutation times this thing. And we got great mileage out of this last time, noticing that this is a polynomial in the indeterminates of degree n. Okay? So actually the degree of this determinant is actually the square root of the number of variables, basically, but okay, it's polynomially related. Same for permanent. Permanent is also like a degree n family with n squared variables. You just don't have this term. And notice that like the definition is actually a formula, but it's a formula of exponential size. So this we certainly allow. And then like the question is like, well, can you do it with a formula or a circuit of polynomial size? Okay, and so actually a big question, in this area is what is the best formula or algebraic circuit size for the determinant and for the permanent? Okay, any questions right now? Okay, so let me come back to the issue of division so that I can get rid of it. So as we saw, like it's actually logical to allow division. It's sensible because it can help in computing various formulas. And of course, if your actually target that you're trying to compute is like a rational function, then you certainly have to allow division. But as we saw, most of the natural examples we were worried about were polynomials. So although division helped here by saving us 1, you might ask, is it possible that division could really help you save like a ton in size? And sort of happily, it turns out the answer is no. Happily, because it means that you can more or less say, without loss of generality, we don't allow division. So this is a theorem due to Strassen. Strassen's kind of a real hero in this area of algebraic complexity theory from 73. And here it is. So for polynomials in n variables of degree d, you can eliminate division from algebraic circuits at the expense of a multiplicative factor of d squared in size. This is actually for either total or non-scalar size. Okay, and so therefore, like, for the most usual setting, like when you're trying to compute a polynomial degree expression, therefore, let me just say, basically, you don't have to worry about divisions. Okay, so if you have any like algebraic circuit, let's say of polynomial size, that's computing a polynomial degree family, then this says, let's say a degree n family, this says that like by making it at most n squared times bigger, you can get rid of the divisions. Okay, and we're henceforth not going to get so stressed about the difference between like one polynomial and another polynomial, just like in complexity theory, all these exact calculations aside. Okay, and so just, this is helpful. You can basically forget about the possibility of division, allowing division. And this looks a little mysterious. It's actually not that hard to prove. I'm not going to do it. It's not super hard, though. Let me just give you the sketchiest sketch. This set of words I'm going to say is like just to kind of convince you that it's like not some like insane miracle like you could imagine what's going on. Like, let's just imagine somebody came up with like a clever algebraic circuit for computing a certain polynomial, but like somehow, for some reason, at some point, it did divide by 1 minus x1. Even though eventually it all canceled out and turned back to a polynomial. Well, again, the highest level idea of how to eliminate this is to replace this by, multiply by 1 plus x1 plus x1 squared plus x1 cubed plus ... well, to infinity. So in some sense, formally, this makes sense. Like, this is kind of the Taylor series of this. Now, OK, you have to check that like things make sense. And of course, there's also the issue that this goes off to infinity. But somehow, and bear in mind, this is a sketchy sketch, since you're like computing something only of degree d, you can somehow truncate this at like d. OK, I'm not saying that you should like now see how the proof works, but like this is like the highest level idea in the proof, and it's not, the actual proof is like not very terrible. So like in general, the main thing that Strassen shows is that like you can efficiently just using plus or minus and times compute like the coefficients in Taylor series of like all the denominators. Okay, so yep.
So this trick is formula, right? Doing that thing, it's d squared.
Yeah, let's see.
Like, does division ever help you in formulas?
That's a good point. I think the answer is no, but let me double check that. Like, I think this equally holds for formulas and for circuits. Like 95% sure of that, but I'll double check. Okay, so I want to, not prove it, but the first, 5 times I heard this fact in my life, like nobody ever told me the proof, and I thought it was like some miracle, but it's not like that crazy. Okay, so having Strasson's division elimination is nice, and one simple bonus of it concerns the determinant. So we normally think of like determinant as like sort of easy to compute, but if I was like, okay, give me an algebraic circuit for it, like maybe it's not so obvious what to do. I mean, this is certainly exponential. But using this, you can get that like a determinant n by n has algebraic circuits of poly n size. So why is that? Well, how do we actually normally efficiently compute the determinant? Do it using Gaussian elimination. You do Gaussian elimination on the matrix, turn it into a diagonal matrix, and then it's like the product of the diagonal entries. So actually, in the bit complexity model with Turing machines, you actually have to worry like a lot about like how big the numbers get and how to represent them with bits and so forth. Luckily, in algebraic circuit complexity, you don't have to worry about that. But on the other hand, it's not like a programming language. You don't really have like ifs or anything. So you have to think about it a little bit. But Gaussian elimination can be implemented with an O(n) cube size algebraic circuit using plus or minus times and division. Because if you kind of remember a little bit how Gaussian elimination works, you have to like to cancel out an entry to make it 0 in a column, you multiply by like the ratio of 2 column entries and like add the negative of it to cancel it out. Anyway, if you naively do Gaussian elimination, it takes about n cubed operations, but you use division in them. But then you could, pardon me?
What do you do with 0?
Yeah, what do you do with 0? Like basically, I mean, the short and glib answer is like you don't worry about it. Like imagine you're doing it on generic matrix entries. Like one way you can kind of rationalize it in the normal English sense of the word rationalize. Just like imagine you're like applying it to like generically chosen or randomly chosen numbers. So you basically never get zeros. And like the formula or the circuit you eventually construct with like plus or minus and times and divide will like correctly compute it on the determinant on like almost all numbers in some sense. But then like it has to be correct on all numbers because it's a polynomial ultimately that you're computing. So basically, if you do Gaussian elimination, just as like a look at what the algebraic circuit is computing in like a formal way, like in terms of formal polynomials and rational polynomials, it'll eventually like everything will cancel out and you'll get like this polynomial. Okay, and then you
cannot apply it for like computing the determinant, right?
Over numbers, no, in some sense. But then you can eliminate the divisions using Strasson and get like a polynomial size circuit, maybe a size like n to the 5th or something, that only uses plus, minus, and times. Now actually, this is a little bit roundabout. There's more direct ways to just do it with plus or minus and times. But they're like a long homework exercise involving, it's not in the homework. Characteristic polynomials or thinking about the inverse of matrices. So like you can do it, but like this is sort of once you know the Strasson's fact, this is like the direct way to think about it. Okay. In fact, the smallest size algebraic circuits for computing determinant are of size n to the omega, where omega is the matrix multiplication exponent, 2.3, blah, 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 whatever. You can somehow reduce matrix determinant computation to matrix multiplication. OK. Cool. Now, actually, since I have the word formula size up here, let me come back to that. This actually produces algebraic circuits, this method. I guess even before Strassen, like you use circuits in computing the determinant with Gaussian elimination. And you might ask about what is the formula size for computing the determinant. Here's the exponential size formula. Now, it turns out that there's a general fact about formula size, which is that if you have a small algebraic circuit for a polynomial degree family, then you can turn it into a pretty small formula that computes the same thing. More specifically, this is a theorem due to Iafil, and also made it a little bit better in a paper by Valiant and a few others back around like 1980. And their theorem is that if you have an algebraic circuit of size S and computing something of degree D, then you can convert it to an algebraic formula computing the same thing of size S to the order log D. And I'm also not going to prove this. Again, it's not terribly hard. Like the Valiant paper that does it is like 4 pages long, and maybe the first page is the introduction. Yeah?
Preliminary.
Yeah.
So like the reason why you can't just use the sort of Gaussian elimination for determinant is just because you might divide by 0 or something?
Well, it's not divide by 0. You can use it. It has divisions in it. Again, you should really try to think about it as all working like with formal polynomials and formal rational functions. But I guess what I'm saying is if you imagine what the Gaussian elimination algorithm does with like numbers as inputs, and just kind of write down what it does with the circuit, which you can, you'll get a circuit that computes the determinant as a formal polynomial.
Yeah, I guess all I was asking is like, corollary seems like, oh, it has algebraic circuits of Polygon size. So it seems like you get that already by just using Gaussian elimination. You don't have to apply stressing at all. Like, I was just asking, like, why are you bothering?
Yeah, good point. I should have said, even without divisions. OK, so this first fact like establishes it with divisions. And then like you can also, if you want, which I kind of in life always do kind of want, because these divisions are annoying. If you want, you can also eliminate the divisions. Thanks, I did not write that very clearly. Good. OK. Again, I will not prove this. It's not terribly hard. Like, it's one of these things where you have like a circuit, and you like look at its pieces and kind of rebalance them. And OK, you get this. So in particular, determinant right has degree n. So if S is poly and the degree is n, this is like poly to the power of log n. So we can conclude, therefore, that like the n by n determinant has quasi-polynomial size formulas. Again, with just plus minus n times. And henceforth, when I say quasi-polynomial, I mean n to the polylog n. But actually, I mean, in this particular case, it's better. It's actually n to the log n. OK, and in general, if you're only concerned about polydegree families of polynomials, then this degree d is polynomial, so this exponent is like log. So therefore, for these p families, quasi-polynomial size circuits are equivalent to quasi-polynomial size formulas. Okay, so this is just to say that like if you're a little bit chill and instead of focusing on polynomial size, you focus on quasi-polynomial size, then it's kind of convenient because circuits and formulas are actually the same. They have the same power. Yep.
Is the upper bound for formula optimal?
Great question. For the case of determinant, it's not known if there are formulas of polynomial size. So n to the log n is the best formula size we know. And that's a great open problem. I think the answer is believed to be no, that you need formulas of size n to the log n to compute determinant. There's a paper by Ron Raz, which was quite great from a little over a decade ago, which says that determinant is not only of degree n, but it's actually multilinear of degree n. There's no variable raised to a power bigger than 1. And so if you're computing the determinant with a formula, it's kind of also natural, maybe, to never introduce powers that are bigger than 1. Now, maybe you should, right? Like maybe there's some clever way to go to higher powers and subtract and cancel them all out. But it's kind of natural to not do that. And he showed that if you restrict attention to like multilinear formulas, which you have to define, but basically it means they don't incur powers that are bigger than 1, then determinant requires n to the log n size formulas. But it's not known in general. OK. So that's determinant. And this was all to kind of tell you that in this model, computing determinants is easy. It has polynomial size circuits, even without division. It also has quasi-polynomial size formulas. So if you don't worry too much about the difference between poly and quasi-polynomial, then it's easy. But what about the permanent? This is, like in the Boolean world, this is like a very interesting case. And it seems much harder to compute than the determinant. So the naive way to compute it requires about n factorial size. I mean, you can get an n to the factorial size formula even, like literally from the definition. It's like the sum of like n factorially many terms. OK, each of size n. You can actually do better than this. This is quite an interesting result, well-known result due to Reiser from '92. He gave formulas for it of size basically 2 to the n. Which is pretty cool. It's still exponential, but like instead of being like n to the n, it's 2 to the n, which is pretty neat. And that's the best thing known, I believe, even for circuits. This n squared times 2 to the n. OK, and so therefore, like it turns out, and I'll expand upon this in the rest of the lecture, the question of whether the permanent has polynomial size or quasi-polynomial size algebraic circuits is perhaps the biggest open problem in the world of algebraic complexity theory. OK, so let's in fact talk a little bit about algebraic complexity theory. I've kind of set up the model, and now we can define some classes. OK, so the first one is called, I'm going to use the terminology that Valiant originally used, which is like algebraic P. Well, OK. Anyway, something like this was in his paper. Actually, following the textbook, Arora and Barak, I'm going to throw in /poly just to remind everybody that this is a non-uniform model. We're talking about circuits. They don't have to be uniformly generated. This is also known in the literature as VP. P for polynomial, V for Valiant, who invented it. But I'm going to use this terminology. And this is like the class of all poly-degree families. So classes of polynomials computable by poly-size algebraic circuits. Okay, so probably the natural definition. OK, so for example, determinant is in this class. OK, yep.
Do we make them be poly-degree families if they're poly-size?
Yeah, it's just a convention that somehow it was decided that it's kind of nice to only worry about computing polynomial degree families. With circuits, you can compute exponential degree polynomials. I guess mainly because like the interesting cases tend to be polynomial degree, like determinant, permanent, multiplying matrices, multiplying polynomials, computing DFT. Also, it's to like kind of give formulas a chance to be competitive. I mean, a formula cannot compute anything of a super polynomial degree. But yeah, you didn't have to define it this way. Let me just also, because of this issue, like I might sometimes also write alg QP/poly, where this Q is standing for quasi. And it's the same definition, but with quasi-polynomial sized circuits. And one reason to do that is then you can say, for this class, it doesn't matter if I write circuits or formulas. That's sometimes convenient. OK, so that's like the algebraic analog of P. Now I'm going to tell you the algebraic analog of NP. Well, it's sort of the algebraic analog of NP. NP is in the name. It's really more like an algebraic analog of sharp P, but somehow the name stuck. And this definition is a little bit weird, so it'll take a little getting used to. But so this class, algebraic NP/poly, which in the literature is sometimes called VP. Again, VNP. Again, for Valiant, is it's the polynomial degree families of polynomials Fn, which is expressible as, and what I'm going to write here is kind of reminiscent of the definition of sharp P, where you have a non-deterministic machine, and like you count how many computation paths or choices for the non-deterministic bits make it accept. I guess it's also sort of like the definition of NP, where you just have a verifier and you take an OR over all the computation paths of whether they accept. Anyway, let me write it. It's expressible as f of x equals the sum over E1 through EM, all ranging in 0, 1. These are scalars. Of G n plus m of like x1 through xn, and then E1 through EM, where G is in P, basically. This family is in alg P/poly. OK, so let me expand upon this definition a little, because it's sort of a little weird. Well, it's not that weird, but OK, so it's again, like it's a polynomial. It's in alg NP F if you can kind of represent it by like an efficient circuit computation, but then like summed over all 0, 1 possibilities for some of the variables. And why? Well, again, it's kind of like the definition of NP. In NP, you kind of like take the OR. I mean, the classic. You take the OR over all. These are like the non-deterministic bits. This is like a polynomial time computation. This is what the real thing you're trying to compute. This is the polynomially many sort of non-deterministic bits, and you take the OR over them. So Valiant was like, well, OR is kind of like sum, so we'll call it alg NP. Really, as I said, it's a bit more like sharp P, where you take in sharp P, you really take the sum over all choices for the non-deterministic bits of the 0, 1 outcome of G. OK, so basically I'm saying, despite the name, you should maybe think of it more like an analog of sharp P. But it's, I guess, like the most natural analog of NP as well in the algebraic complexity world. OK. Let me tell you a few facts about this. Oh, this is like a small fact, which it's good to know. Sort of a technicality, but it turns out definition of alg NP/poly is unchanged if you insist that the G's are formulas. OK, so I allow you circuits, but actually, and again, it's like a theorem. There's, I don't know, like a couple pages to check, but like you can always do it with a formula. And somehow this is reminiscent of some other times tricks we've seen in like complexity theory, where like once you kind of allow like non-determinism, you can kind of simplify some computations. Yeah.
Did you get to specify what m is as a function of n?
Oh yeah, sorry, I did not write this. This is a crucial thing. M has to be polynomial in n. Sorry about that. Yeah. So it's like really if f is in alg and p/poly, if there exists a function m, which is polynomial in n, and a family g, which is in alg p/poly, or the version with formulas, such that this identity is true. Thanks. That was a crucial missing aspect of the definition. OK. This is not like a super important comment, but I thought I'd let you know it. OK, so another reason this class turns out to be natural is that some natural problems are in it. OK, so for example, the permanent, and hopefully maybe you were expecting this, and also let's say the problem like counting the number of Hamiltonian cycles in a graph. These are in alg NP/poly. Okay, and let me prove that to you for the case of permanent. Okay, and it's a pretty simple proof. It's kind of cute. Okay, so I'll write an expression for permanent, and then you might see where I'm going with this. OK, so for permanent, the definition is like the sum over all permutations. There's no sign. It's just this. Product I equals 1 to n of xi sigma I. And let me write this like this. It equals the sum over all 0, 1 matrices. I kind of want to sum over all permutation matrices of like the dot product of E with X. So I'm going to write this weird expression. Is permutation matrix E times product over I and j, Eij, Xij. So what do I mean by this? I'm going to construct some expression which is 0 or 1, depending on whether E is a permutation matrix, meaning one that has like exactly 1, 1 in each row, exactly 1, 1 in each column, and is otherwise 0, like the natural matrix representation of a permutation. And if I can do that, then this expression does compute the permutation, because like it sums over, effectively it's summing over all permutation matrices of the product of the entries of X in the places where the permutation matrix has 1. And you see this exactly does look like the definition of algebraic NP. We have like n squared. Here m is n squared, different 0, 1 values that we're summing over. And so basically it suffices to show that this is in like alg p/poly. Okay, because this is also, this is like, I don't know, polynomial number of multiplies. Actually, that's it, like a polynomial number of multiplies. Does that make sense? And it kind of works. You could finish the job at this point. Kind of works how you would expect. Is permutation matrix E. I can kind of express that as follows. All right, I'm going to say that this is the product. I goes from 1 to n of something called is exactly 1 of EI1 through EIN. That expresses that there's exactly 1, 1 in the ith row, but also I need it in the columns too. So E1i through ENI. So this is like a polynomial looking thing, actually like a product that does indeed sort of check if E is a permutation matrix subject to this thing being expressible as a polynomial. And that's pretty easy. If I want to check if n numbers are have exactly one of them 1, it's just this. It's like sum over all I, ci times product over all j not equal to I, 1 minus ci. And I guess what I should really be emphasizing here is that like these things are all semantically correct, assuming the inputs are 0, 1 values. Okay, which they're ultimately going to be in this setup. Okay, this checks that ith one is 1 and the rest are not 1. Okay, and this is also a polynomial size formula. Okay. So, good. So we've got this analog of NP, algebraic NP. It contains permanent. It contains other problems that are like sharp P kind of problems, like sharp Hamiltonian cycle. Given this technology, you could, I think, easily figure out how to compute that. There, the input is like the adjacency matrix of the graph. Okay, so as promised at the beginning of the lecture, one of the culminating results in this area is Valiant's theorem that the permanent is complete for this algebraic NP class. Okay. Now, in order to understand what completeness means, we have to talk about reductions. And in the context of algebraic complexity, there's a very specific kind of reduction that's used. And it's used because it's a very demanding form of reduction, but it works. Like all the completeness results you want to prove, you can use with this very demanding form of reduction. And here's what it is. We'll say that like f of x1 through xn, that's a polynomial, is a projection of some other polynomial, gy1 through ym, if, let me just say you can get f from g by plugging in xi's and constants for the y's. Okay, so for example, let's see if I can do a little example on the spot. F of x1, x2 equals x1 plus x2 is a projection of g equals y2 squared y3 plus y1. And why is that the case? Well, the projection is take y squared to be the constant 1, take y3 to be x2, and take y1 to be x1. Okay, if you plug these things into G, you get f, if I did it correctly. Okay, and you can use, down when you're plugging into y, you can use the variable x multiple times. You can use scalars multiple times, etc. Okay, so basically, it's like if you have an algebraic circuit for y, you can get for G, you can get one for f by literally just kind of fixing the inputs to some G's inputs or scalars in a certain way. So as I said, this is quite a restrictive notion. It's quite a restricted way to say that oh, you can compute f efficiently if you can compute G efficiently. But it just turns out in this context of algebraic complexity, this is often the way you can do it. And so therefore, typically, completeness is defined with respect to this. So we'll say that a family Fn projectively reduces to a family G of n. I'll optionally put a Q here for quasi-polynomial. If there exists, a function m of n, which is poly n, or if I'm allowing quasi-polynomial in n, such that f of n, this family, is a projection of G m of n. Okay. Yeah. So why do I say that this projection is kind of good enough? Well, here's something that is on your homework. If f has a formula, an algebraic formula of size s, it's a projection of the determinant, let's say m by m, where m is, on your homework, I asked you to prove 3s minus 1. So practically S. In fact, you can get it down to S plus 3, but you don't have to. And this is actually an amazing fact. It says like any mathematical formula can be expressed basically as a determinant of slightly larger size. And arguably this expresses, I mean, it's the reason why determinant is like the most popular polynomial in all of mathematics. It shows up everywhere. It's like Jacobians and Wronskians and Alexander polynomials. These are all, you know, given by determinantal formulas often. And like in a math textbook, they'll say like, oh, here's some polynomial we're trying to compute, and like, look at this amazing formula for involving a determinant. Like, isn't that awesome? In a sense, no, it's not so awesome, because whenever you have any formula at all that's like simple, you have a determinant formula that's also equally simple. Yep.
Just to clarify on the reduction case, so like, I guess you're saying you can basically plug in polynomials with the x side, but you probably want to say they're down to 10. You want to plug in like super high degree polynomials with x size when you do these projections?
Yeah, in fact, you're not even allowed in the definition to plug in polynomials, just single variables.
Okay.
Single variables or single scalars. Yeah. Usually it's okay if you plug in, you know.
You could imagine it's like taking a small circuit for like the x size and feed that into the circuit G, and that's sort of like reduction.
Yeah, so you could do that, right?
That's not how it's designed.
Yeah, that you could make that the definition, and then you would still have the property that like if G has polynomial sized circuits, then so does F. But like, nevertheless, like it's decided, and it turned out to be a good idea to take this extremely strict form of reductions. Okay, so this is like a cool, I mean, this is a really cool fact that I kind of love. And a consequence of this is that the determinant family is basically complete for algebraic P. It's complete technically for algebraic quasi-polynomial size circuits. It'd be good if we could just write polynomial here. We can't quite, but so why is that? Well, as we saw, determinant has polynomial size algebraic circuits, so it's in this class. And on the other hand, if you have any thing with quasi-polynomial size algebraic circuits, then this trick that reduces circuits to formulas shows that it has, you gain a factor of log n in the exponent, but you have quasi-polynomial size formulas. Then this homework fact shows that that thing is a projection of determinant with m being quasi-polynomial in n. Okay, so everything that has quasi-polynomial size circuits is a projection of determinant of quasi-polynomial larger size. I guess this should just be like under, you know, Q projection reductions. Okay, so that's kind of nice. Again, if you're a little bit chill about like the difference between polynomial time and quasi-polynomial time, this shows that determinant, which is like a sweet family of polynomials that everybody likes, is complete. Okay, and now you might expect this punchline that I mentioned. It's the theorem of Valiant. Again, he was very productive in '79. He also invented pack learning that year. It's pretty good. The permanent family is complete under projection reductions, not quasi-polynomial ones, for alg np slash poly. And the proof, which I'm not going to do at all, unlike the p to the sharp p proof, which I will eventually do, you know, it's painful. I don't know. It's gadgets. I mean, it's gadgets. You'll see like an example of kind of like gadgety proof in this homework problem. Let me also mention, I'll take your question in a sec. This is over any field. You know, at beginning I said just fixed complex numbers, but you know they worry about other fields if you get really into it, or any field with characteristic other than 2. Because when the characteristic is 2, you can actually compute permanent efficiently using the determinant. Yeah.
Why did you say that we needed quasi-polynomial productions when the determinant is complete?
I guess you don't need it. Yeah, I mean, it's true, I think, whether I write quasi-polynomial or just polynomial here. Yeah, I guess it's there. Therefore, it's better to write polynomial, actually. OK. Actually, Birgesser showed that like over any field, characteristic 2 or not, counting the number of Hamiltonian cycles is algebraic NP complete. OK, and therefore, I mean, you know, the algebraic analog of P versus NP, which is whether algebraic NP slash poly equals algebraic P slash poly. Well, let's just put a Q in here, quasi-polynomial, to make the following statement a little neater, is, you know, by the theory of completeness, literally identical to asking whether the permanent is a projection of the determinant. And by M, for M, you know, you can ask, I guess, quasi-polynomial size. In other words, you know, if you want to compute the permanent of n by matrix, is it possible that it's always equal to the determinant of some like kind of slightly larger matrix, polynomial or quasi-polynomial? And of course, Valiant conjectured that the answer is no, and that's what people typically conjectured, but this is unknown. Okay, so we know, I guess, that like you know, you can take m to be like basically 2 to the n because of Reiser's formula, but that's all we know. And what's really great about this formulation, there's several things great about it. So this is like sort of like the P versus NP problem in algebraic complexity, but it's equivalent to this statement about permanent versus determinant, and that statement has like no computation in it. You don't need to know what a Turing machine is. You don't need to know what like bits are. Like it's a statement you can just like tell a mathematician, and you know the mathematician will say, yeah, that's a cool problem, and you can say, aha, it's basically equivalent to P versus NP in the algebraic model, which is really quite cool. And indeed, this problem was thought about like long before Turing or anybody, like 100 years ago. So like Poya, is that the right accent for Poya? And Sego. Separately in like 1913, they thought about this problem. And in fact, they were not even able to show that you can't do it with m equals n. That's what they like tried to prove, and they couldn't even do that. They proved that like you couldn't do that if you're like only allowed to substitute in like plus or minus variables. Okay, so it's like a problem with like a long pedigree, and it's kind of cool that like it's just equivalent to like the P versus NP problem in algebraic world. Right. So I'll tell you a few more things that are known about it. Joachim von Zergotten, there's several works on this, but I'll just tell you two. In '87, he managed to show that m has to be at least 1.06 times n. Okay, this is like kind of reminiscent about like all the like kind of patheticness that we have in complexity theory, where like slightly, not even superlinear, like a slightly better than m trivial bound is known. Actually, there was a kind of awesome result in '04 by Mignon and Resser. They show that m has to be at least a half n squared. Yeah, pretty good. They got it up to n squared. Okay, really, we maybe think it should be exponential or at least super polynomial. Hey, this is better than nothing. Okay, and they'll use some like algebraic geometry. It's actually not that hard to understand, though. Good. Okay, the last thing I'll say is the following. Yeah?
Did they prove that P is not equal to NP? Was that implied?
Great question. That is strictly easier than proving P does not equal NP. So I'll end here, and I'll prove this little fact next time, because it's nice to see the proof, because it uses like 5 things we proved already, like Toda and Karp-Lipton and so forth. But this is a theorem. If P does not equal NP, that implies that algebraic NP slash poly does not equal algebraic P slash poly. And now let me add like 2 funny caveats. Like this is actually over any infinite field, such as C or Q, you need to assume the generalized Riemann hypothesis. But don't worry about that. Basically, I'll mention why like next time. It's this like a little annoying twist. But this is true. So that's a connection. So what this says is, like, suppose your goal in life is to prove that P does not equal NP. Well, it's strictly easier to prove that algebraic NP/poly does not equal algebraic P/poly. So maybe you would say, try to do that first. And then, in turn, that's equivalent to asking this permanent versus determinant question. So it's like a great way to motivate complexity theory for a pure mathematician. And OK, we'll see the proof of this next time. It's almost super easy, combining like all these theorems we know. The only like annoying thing is like in the algebraic circuit model, you can have like arbitrary constants, which might have like super polynomially many bits in them, even if they're like rational numbers. So like in order to deal with that, you have to like hack around. OK, so I'll see you on Thursday.